This is Lecture 1 for Module 12 in the book Problem-Solving Guide for Electromagnetism and Optics, Light as a Wave. In the previous two modules, we treated light as a ray, a beam. In the 1700s, the nature of light was a big mystery. What is it? Does it have mass? Is it a wave, a disturbance in a medium, or is it a particle? If light was a wave, it would produce constructive and destructive interference just as water waves and sound waves and other waves do. Waves that are in phase add. So the red and the green wave are shaking up and down in phase. They start up, the green starts up, and when they meet, they add because they're 100% in phase. They overlap completely. If the waves that are out of phase by a half a wavelength, they cancel each other out. So we're going to shift the green wave by half a wavelength. And here, the red goes up and the green's going down. If I superimpose these, I get a flat line. So if the waves are half a wavelength out of phase, you get nothing. Particles don't do this. So the green wave is shifted. It's delayed or advanced by a half wavelength. Here's the wavelength right here. It does this, and then it does it again. That's the definition of the wavelength. If you shift it by half, we're moving this point over here. Shift it by half a wavelength, they destructively interfere, and you get nothing. Here's a couple diagrams that show the constructive and destructive interference of water waves. The sources of the waves are two bobbers right here. They're driven up and down at the same time with the motor. They're in phase. They go up together, they go down together. And you get this pattern. If one wave has a shorter distance to travel to any point in this plane on the water, the waves will be shifted in phase because there's a path difference. They're not in phase anymore. If the path difference is an integer number of wavelength, if they're shifted by exactly 2 wavelengths, they're going to be back in phase. They're going to interfere constructively. If there's an odd number of half wavelengths, the waves will interfere destructively. One will be high and one will be low, and they'll cancel each other out. So a half a wavelength is destructive interference. 3/2 of a wavelength is destructive interference. 5/2 of a wavelength is destructive interference. There's a continuous degree from constructive to destructive, but we're going to be focused only on either destructive or constructive in this module. Since this is an important concept in this module, let's try to really understand it. So I'm going to give you some points in the water, and you tell me the path difference. Here's one right here. This point right here. Let's think about this point. We can measure the distance from the source on the right to that point. It's 9 wavelengths. We can measure the source from the distance from this source on the left to the point. That's 9. This is 8.5. There's a path difference, and it's a half a wavelength, which means the waves are going to interfere destructively. So if you took a small bobber and put it right here, it would barely be bobbing. The waves interfere destructively. They started out in phase at the bobbers, but they're shifted and interfere destructively. You get almost nothing. If we construct an isosceles triangle, by drawing a line, we can see the path difference. So here's our isosceles triangle. This length of this triangle side and this length of this side are the same. Here's the path difference right there. And that path difference is a half a wavelength. And that's why they interfere destructively. Now let's consider a different point. This one right here. If I get the distance from the source on the right, it's 10 wavelengths. Source on the left, it's 9 wavelengths. This one has a longer distance to go, but it's longer by 1 complete wavelength. So they're back in phase. If you stuck a bobber here, it would be going up and down wildly. The waves interfere constructively. They're shifted by a full wavelength, just like that. And we can construct an isosceles triangle again, drawing the line over. These two sides are equal of this triangle, and here is the path difference, and it looks like about one wavelength. This module is concerned with getting the path difference and then relating it to the order of the interference. Here the order of the interference is the first maximum from the central maximum, shifted by one whole wavelength. All right, now here's a quiz. In units of wavelength, what is the path difference from each source to this point, right here? What's the path difference? From the right to this one, from the left to this one. What's the path difference? The answer is 0. The paths are the same. The waves are in phase. It's going up and down wildly. What about this point over here? This is the first minimum. The first minimum from the central maximum, the first minimum, has a path difference of a half a wavelength. If I draw a line from here to the right and here to the left, the path difference would be half a wavelength. Here's another one, this one. That's the same order of interference. It's a half a wavelength difference. First minimum, the first minimum from the central maximum. All right, how about this one? This is constructive interference. There's the central maximum. The path difference is 0. Here's the first maximum. Path difference is 1 wavelength. Here's the second maximum. The path difference is 2 wavelengths. Second maximum. How about this one? What is this? Here is the central maximum. Half a wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths, 2.5 wavelengths. So if I drew a line from here to here, and the right side, R2 is 2.5 wavelengths longer than R1. Last one, how about this guy? Way over here on the right. That's the central max, first min, first max, second min, second max, that's the second max. Path difference is 2 wavelengths. All right, you want another one? One more? All right, how about this guy? Right down here. This is actually a maximum. I put it in the trough, but that's a deep trough. It's going up and down, up and down, up and down wildly, right here. That's the central max, first max, second max, third max. The path difference is 3 wavelengths, and you can see if you look at the horizontal distance between these two bobbers, it looks like about 3 wavelengths. 1, 2, 3. This is water. What about light? Is light a wave? Does it interfere? In 1801, Thomas Young performed the double slit experiment, and light produced an interference pattern. And here it is. Light, dark, light, dark, light, dark. So this dark spot, what we say is, here comes the light going through this slit, and light going through this slit is out of phase by a half a wavelength. One is up, one is down, and it's dark. Photons are getting here from both slits, but the photons cancel each other out, apparently, and that's why it's dark. We can do this easily in a lab. We do this in physics. But if light is a wave, what is the material that is waving? You can't have a water wave without water. You can't have sound without a medium to travel through. Sound doesn't travel through a vacuum. Sound isn't an entity in itself. It's a disturbance of a medium. You can't have a water wave without water. A water wave isn't a real entity. It's a disturbance of the water. But we know light can travel through empty space because we can see the stars. Is light really a disturbance in a medium? Is it a wave? every experiment we have done with light since the double slit, and every experiment that looks at dim light provides evidence that light's a particle. It looks like a particle. The photoelectric effect, it's a particle. Ultraviolet catastrophe, it's got to be a particle. That's the only way you solve that ultraviolet catastrophe. Photomultiplier tubes, they count photons. If you turn down the light so it's very dim, it will click, tick, 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 as if particles come into it. It's not a hum, it's a click. It doesn't look like there's a medium that's being disturbed. But we still have this double slit. It looks like light's a wave. We can repeat the double slit with modern equipment using a laser and photomultiplier tubes instead of a screen. To shine the light on, the photomultiplier tubes will count the photons. When we turn down the intensity to 1 photon at a time, and we can do this, we shoot 1 photon, we wait for a photomultiplier to click, then we release another photon. We still get the interference pattern. And here's a single photon double slit apparatus. Baldwin-Wallace has one of these. Single photon double slit, we still get the interference pattern. So how the heck can we call it interference if there's only 1 photon there at a time? Richard Feynman got the Nobel Prize for his quantum electrodynamics, his explanation of how photons and electrons behave. And he says light comes in this form, particles. It's very important to know that light behaves like particles, especially for those of you who have gone to school, probably were told something about light behaving like waves. I'm telling you the way it does behave, like particles. In this module, we're going to use the wave model of light because it works. We can calculate where the dark spot's going to be, assuming light's a wave. Even though the guy that got the Nobel Prize in physics told us, look, it's not a wave. So we use geometry to calculate the path difference, and then we use the wave model of light to say that's the second maximum. If the paths aren't virtually parallel, we can calculate the path lengths using the Pythagorean theorem. If they're virtually parallel, you can make some assumptions, and we're going to do that. Let's start with the Pythagorean theorem. This is problem 12-3 in the textbook. There's a microwave. There's a microwave detector. The slits are 10 centimeters apart. Microwaves are on the order of a couple centimeters. The distance from the slits to the screen is 50 centimeters. This detector, 12 centimeters above the position of the top slit, is detecting the second minimum. So we start at the central max, right across from the source. There's going to be a maximum there. That's the central max. We start moving up. We get to the first minimum. We move up a little bit more. We get to the first maximum. Move up a little bit more. We get to the second minimum. The second minimum, the path length difference is 3/2 of a wavelength. So we're going to calculate the 2 path lengths. The first path length is pretty straightforward. The short path length is from here to here, the top slit to this point. That's 50 centimeters, that's 12 centimeters. We can use the Pythagorean theorem, and we get 51.420 centimeters. The bottom one's pretty straightforward too, because the distance between the slits is 10 centimeters. That makes the total vertical distance 22 centimeters. So we have 50 centimeters, 22 centimeters. And there's that second path. That's a little bit longer. And I can draw an isosceles triangle and get the path difference. And we're going to calculate it. So it's 50 squared plus 22 squared, square root, 54.626. That's the long one. So we can just subtract them to get the path difference. But this isn't the answer to the problem. The problem asks for the wavelength. And we know that that distance is 3/2 of a wavelength because it's the second minimum. So we just set the path difference equal to 3/2 of a wavelength, and we solve for lambda, 2.14 centimeters. That's the wavelength of the microwave. So if I draw a isosceles triangle here, I get 1.5 wavelengths right in there, the path difference. So these R1 and R2 aren't close to being parallel. R1 makes this angle's 13.5 degrees, this angle's almost 24 degrees. Now we're going to tackle a problem in which the two paths, R1 and R2, are virtually parallel. This is problem 12-9 from the textbook. We have a double slit. Two slits are very close together, 1/4 millimeter apart. The distance between the bright lines on the screen is 1 millimeter. What is the distance from the slits to the screen? Since the wavelength is so small, the distance between the maxima on the screen is small. That is, to make R2 bigger than R1 by 1 wavelength, which is 660 nanometers, 660 times 10 to the minus 9th meters, you don't have to go too far from the central maximum. To stretch R2 so it's 1 wavelength longer than R1, you don't have to go up so far on the screen because the wavelength is so small. To really understand what's going on, you have to zoom in on the slit itself. It's hard to see these slits because they're so close together when you look at this scale. So let's really zoom in on the slits. So here's the upper slit, here's the lower slit. That's 1/4 millimeter apart. And these guys are heading, both of these waves are heading to the first maximum, which is 1 millimeter above the central max on the screen some distance away. And this is really not the scale because the wavelength is 1/400th about of the distance between the slits. So to draw the actual wavelength would be really hard. You couldn't even see it at this scale. And because of that, this angle is exaggerated significantly. It looks, you can see that this line is actually going up. But to scale, remember, the first maximum is 1 millimeter apart on the screen. So these lines are going to be, they would look horizontal if I drew them to scale because the wavelength is so small. The diagram does show that the paths are parallel, virtually parallel. The waves start 1/4 millimeter apart. They meet at the first maximum, 1 millimeter above on the screen at some distance away, which we're going to calculate. To calculate the path difference with this geometry, we're going to add a line. We're going to make an isosceles triangle, just like we did before. And there it is. This dashed line makes an isosceles triangle. These are virtually right angles because this triangle is so sharp. The path difference is 1 wavelength, as we can see right here. Starts low, goes up, goes back down. There's 1 wavelength. So from this slit to the screen, there's a bazillion and 1 wavelengths, and from this slit to the screen, it's a bazillion. That's why it's the first maximum, shifted by an integer number of wavelengths. The path difference is the short side of this triangle. So if we draw this triangle, there's the hypotenuse, that's the distance between the slits, and this is the path difference, this side of the triangle. We can calculate the small angle at the tip of this triangle because we know what the slit distance is, 0.25 millimeters, and we know what that distance is. It's the 1 wavelength of light, 660 nanometers. So sine theta, even though it's not exactly a right angle, we're using sine theta. That's the opposite side. That's the hypotenuse. And we convert to meters or whatever you want to convert to. They have to have the same units. And we get 0.00264. That's sine theta. We can take the arcsine to get the angle in degrees. It's 0.15 degrees. It's a very small angle. Virtually horizontal. Since the angle is small, we can make an approximation. So here is our approximation. If we go to the central max and we go to the first max, there's an angle theta there that's going to the first max. And the tangent of that angle is 1 millimeter. Remember, the first max is 1 millimeter above the central max. And the adjacent side is the distance to the screen, which is what we're after. So tangent of this angle is 1 millimeter, the opposite side, divided by d. So there's the triangle, and we have the angle, so we can calculate it. 378.79 millimeters, which is about 38 centimeters. The two paths aren't exactly parallel, which means that the blue triangle is not really a right triangle, so this answer is not exact, but it is damn close. And we can see how close it is by actually calculating the distance. We can use the Pythagorean theorem to get the path lengths. Remember, the first maximum is 1 millimeter above the central max. So this is R1, it's a little bit shorter. So if we go from the central max, this is 1/8 of a millimeter from the center to the first slit, and this is 1/8 of a millimeter from the center to the bottom slit. So the long distance is this vertical distance is 1 1/8 millimeters, and then we have the d squared, and then we have 7/8 of a millimeter for the top slit for the vertical distance, and the horizontal distance is d, and we can set this equal to the wavelength because the path difference is 1 wavelength. We have to solve this equation for d. It's not fun. I didn't even do it. I just looked it up. I used Wolfram alpha, and it gave me a d of 378.78 millimeters, which is almost exactly what we got before. It's a very good one. So in general, when the path R2 and R1 are virtually parallel, a good approximation is d sine theta. So there's the d, and there's the angle. So d sine theta is the path difference. Sometimes we ask for the path difference, sometimes we give you the path difference, ask for the distance to the screen, whatever. There's one unknown. So, practice. What you're going to be doing is calculating the path differences with some geometry, and then relating the path difference to the order of the interference, the wavelength. Is it second minimum, second maximum, whatever. Have fun.